Hello, this is Professor Dan Kernler, casually attired today because I was out playing with my kids in this nice weather, but trying to do a quick video, finish up chapter 16, or 16.2, I should say, section 16.2. In this video, we're going to finish the last 3 pages talking about double integrals over general regions. So let's pop in here, get back into the notes. Recall we had talked about this simple integral from 1 to 5 dx. It really means the length of the interval, so you can think of that going from 1 to 5, and it's the length of that interval, or it's the area of the region above that interval below the curve y is equal to 1. So you think of this, you could have 1 to 5, y equals 1, and it's this area right here. So likewise, in 2 dimensions, we can think of the integral from 1 to 5 of the integral from 2 to 3 of dx dy means area of the region. We'll do a quick sketch here. X is going from 2 to 3, and y is going from 1 to 5. So it's that area, or it's the volume of the solid above that region below the plane z is equal to 1. So famous last words here, but let's see if we can do a quick sketch of that. So x is going from 2 to 3, and then y is going from 1 to 5. Our domain is then that rectangle in the xy plane, and then we're going to be below the function, the plane z equal 1, which means we're going to end up with a rectangle, or sorry, we're going to end up with a box there. So the extension then is that one would think that the double integral of a function means volume above the region given by the limits, but under the surface z, which is some function of x and y. So what this would be is we have some region in the plane. So if we're going to go from 2 to 3 on the x and for 1 to 5 on the y, here's our domain. And then we have some z function above that. Maybe let's try a different color here. So z is some surface up here, right above that. If we go and extend up to the surface, we might have some that did not look good, but some 3-dimensional region like that. So we have some volume under this surface z equals xy. So just kind of wrapping it up and comparing 2-dimensional integrals to 3-dimensional integration here. All right, so another comparison. We can visualize the integral from a to b of f of x, or you can think of that the integral over some interval to mean kind of the filling out of a 2D area above that 1D interval, right? So you have some a to b, you have the function above this y equals f of x, and so what you're doing is you're really filling out, we have all these rectangles, you're adding them all in as you go, and that's going to give you the area underneath it. So what you're really doing is you're filling out the area under the curve by varying height vertical lines. And they're going to end up filling in that whole interval. All right, so what about double integrals then? So what we can do is we can visualize double integrals over a region to mean the filling out, kind of casually filling out the 3D volume over your 2D region by varying height vertical planes. And what this means then, I didn't really leave enough space for a picture here. You have some region in the xy plane, you have some surface above this, And what you have is you can go up to the surface and you have this plane there, and you're going to add those up and kind of fill them out as you go down. That's like that slice of bread, and you're adding up those slices of bread. So we're going to try to do this. We're going to do an example here. We're going to try to practice here switching the order of integration and trying to visualize this where we have this plane and then we're adding up all the planes as we go. All right, so we have a plane. Speaking of planes, we have a plane 6x plus 2y plus 4z equals 12. And we're going to find the volume bounded by that and the coordinate planes. This is going to be in the first octant then, x, y, and z. And let's see, if y and z are 0, x will be out here at 2. Kind of went a little unnecessarily far there. If x and z are 0, y is 6. So we're just finding the intercepts here. And if x and y are 0, z is 3. What we have here then, it looks like a triangle, kind of what we're looking at. That's not a good line at all. A little better. We're looking at kind of the, can I get a visual here with 3 pens? Spur of the moment idea, probably not good. So we have our coordinate axes here, if you can see that. And what we're going to do is we're just going to chop a triangle in that first octant. So that's what we're seeing, is we're seeing that in the first octant. Could have had a maple demonstration up too. Okay, so we're going to do this 2 different ways. We're going to do this by try to integrate x first, and then we'll integrate y first. First of all, let's get z here as a function of x and y. So 4z equals 12 minus 6x minus 2y. Divide by 4, z is 3 minus 3/2 x minus 1/2 y. So that is our function of x and y that we're going to be finding the volume underneath. Okay, so first, let's do this. Let's make a little slice here at a specific x. That will make a triangle. And let's find the area of that triangle. So what we're going to do is we're going to integrate y underneath that. So let me draw a picture of my x, y here in the xy plane. What did x went out to 2, y went out to 6. And so here we have the region. And what we're going to be doing here is we're going to be integrating, we're going to be going, let's see, at a specific x, we have this vertical line right here. And so that area is going to be a function of x. The area is going to be a function of x. And so what we need to do there is we're going to integrate our function f of xy, but we're going to integrate with respect to y first. So we're going to integrate y going from the top to the bottom. And then once we have that, we will add up all of those in terms of x. So let's see here. It looks like y starts at y equals 0. That's 0. And then the end is not so clear. It's the line equation, but in the xy plane. Well, that's when z is equal to 0. So for that line, z is equal to 0. That's the trace, right, in the xy plane. So z is equal to 0. We would get 6x plus 2y is equal to 12. 2y equals 12 minus 6x, or y is equal to 6 minus 3x. So that is what that equation is in the xy plane. And so if we're adding up along that vertically, y starts at 0 and ends up at 6 minus 3x. All right, so then our volume, if we scroll down, volume, make sure, let's see, I've got it right here. Volume will be, let's see, the integral of this area, 0 to 6 minus 3x of f of x. Oh, we have that. This is what I wanted to rewrite it. What that function is 3 minus 3/2 x minus 1/2 y. and we're integrating that with respect to y, and we're going to integrating all of that with respect to x. That's the double integral. And x here, if you see, x goes from 0 up to 2. Okay, so this is a little tedious. Let's pause there, and then let's try the other orientation and just compare setting these up, and we'll see if we can do the integrals. The integrals, the challenge is mainly algebraic. So let's do the other orientation. What's a good color here? Let's switch to green. So we're going to do the other orientation. And so we're going to integrate with respect to x first to get that area, which will be a function of whatever specific y it's at. And then we'll add all those up along the y-axis. I'm going to go do a new drawing over here. X, y, and we have 2 and 6 again. And instead of going vertically, we're going to go horizontally first. And this area now, area will be a function of y, and we're going to integrate x first. So we're going to integrate the function, and we're going to integrate with respect to x. X starts at 0 and ends up at the curve, this line. So just like before, we had 6x plus 2y equals 12. So we can solve for that x value. 6x equals 12 minus 2y. X is equal to 2 minus 1/3 y. So x goes from 0 to 2 minus 1/3 y. Then the volume here for this one will be the integral of, and then we have this integral inside, 0 to 2 minus 1/3 y, and then the function 3 minus 3/2 x minus 1/2 y. And that's we're integrating x, because x started at 0 and ended up over on the line. And then we're going to integrate all of that with respect to y. And we're going to, so we have that horizontal area here. If we look at, that's the green area over on the graph, and then we're going to add all those up in terms of y from 0 up to 6. And so these two integrals should give us the same volume when we are done. Let's just do one of them as practice. Let me do the second one here. I don't want to have this be a crazy, ridiculous video. Let's do the second one. We're integrating with respect to x. That's 3x minus 3/2 x squared minus 1/2 xy from 0 to 2 minus 1/3 y. And we're going to integrate eventually all of that dy. And let's see, integral from 0 to 6. We're going to plug in 2 minus 1/3 y minus 3/2 times 2 minus 1/3 y squared minus 1/2 x. Ooh, I got to scroll to the right here. Scroll down a little bit. 1/2 x times 2 minus 1/3. Oh, no. We're plugging in for the x. 2 minus 1/3 y times y. And then we'll subtract 0 from all of that. And then all of that will be integrated dy. Kind of going off my page here. Oh, you see what I mean about the algebra? Oh, gross. So I don't know how much time I want to spend here. 6 minus y minus, oh, this will be 3/2 times 4 minus, and we double them multiplied together, 4/3 y plus 1/9 y squared. So multiply 3/2 times that, that'll be 12/2, so that's 6 plus 2y plus 1/6 y squared, and then we have minus 1 plus, oh no, minus, there's a y at the end there, minus 1y, and then plus 1/6 y squared. Oy, oy, oy. I'm going to double check with my previous work here, make sure I did all this correct. 6 minus 6 is 0, that's nice. Oh, what? Minus y plus 2y. Oh, this is not what I got before. See, the issue here is when we integrated, let's see here. We integrated 3/2 x squared, but we forgot to divide by 2, so that should be 3/4. This is 3/4. So now, so 3/4 times 4 should be -3. Let's see, well, 3/4 times 4/3 should be plus y. And then 3/4 times 1/9, that'll be negative, 3 and 3 will be 6, 2, negative 1/12 y squared. I think that looks better. Let's see here. So 6 minus 3 will be 3. Okay, that's good. That's what I got before. We have negative y plus y, negative y, so minus y, also good. Negative 1/12 plus 1/6, that'll end up being plus 1/12 y squared. Whew. Okay, that's what I got last time. Just fixed a small little error there. So now integrating with respect to y, 3y minus 1/2 y squared plus 1/36 y cubed from 0 to 6. Let's see, 3 times 6 is 18. 6 squared is 36, minus 2, minus 18. 6 cubed. Well, I mean, 6 squared is 36, so that's going to simplify. You're just left with 6. So we should have 6 when we are done. Whew. Okay. For the other one, well, we don't want this video to be ridiculously long, but that would be good practice for you to try that. The algebra does get obviously tedious here. I missed a simple thing in my integrand there that I forgot to divide by the exponent. That is very easy to do. These are not fun to grade because it's easy to have an answer that's totally wrong, but all your work is right except one small thing. But we will get 6 the other way as well. You can check that integral. And then we did say here, we wanted to try to demonstrate that we could do both orders of integration, but then we could also just use geometry. And so what we have here is a prism, or a pyramid, and for geometry, you can find the volume. It's 1/3 times the area of the base times the height. So for ours, that would be 1/3. The area of the base will be 1/2 times 2 times 6. And then the height is the height, which is z there, that is 3. And so 1/3 and 3 simplify, and 1/2 and 2, we end up with 6. That would have been a much easier way to do it, right? So that is this example, and let's see if we can finish up the video, hopefully not quite too long. We're not actually going to find the volume here for this last one. We're just going to set it up. So last example, set up the double integral that finds the volume of the solid bounded by this ellipsoid. We're going to look at just y being greater than or equal to 0, and it's bounded by that ellipsoid, y equals 0 and z equals 0. The ellipsoid here, if you do the traces, we have z squared equals 1 minus x squared minus y squared over 9. And if we solve to get it in the form we're used to for an ellipse, if we do the traces in the xy plane, we get z is equal to 0. We would get 1 in the x direction and then 3 in the y direction, and we'd have this portion of an ellipse. In the xz plane, y is 0, we actually just get a circle radius 1. And then in the yz plane, if x is 0, we get the other part here. So we have this portion of an ellipsoid. Y is greater than or equal to 0, and we're bound by y equals 0 and z equals 0. Okay, so let's look in the xy plane. And let's see here, set up the double integral. We can choose either one, either orientation. In the xy plane, we have 1 and 3. And I think they're going to be equally difficult because we can't write one as a function of the other. Let's just, since we have our kind of vertical orientation here, and we're used to seeing that. Why don't we just solve for y? Multiply by 9, 9x squared plus y squared is equal to 9. Y squared equals 9 minus 9x squared. And y will be, now normally you'd have plus or minus, right? Normally you'd have plus or minus, but we just had the top half. So that is that curve, and let's draw our piece vertically. So what we're going to do is we're going to add up from the bottom to the top. So we're going to integrate y first. We're going to integrate y, and so we're going to find there's our function, and we're going to integrate that with respect to y. Y starts at 0 and ends up at this curve in the xy plane, which we just found was the square root of 9 minus 9x squared. And then once we get that, that will give us the area. Which way did we go? We went this way. Of that cross section. And that's what we just found. We found the area of that cross section. Then we're going to add those slices up and kind of fill that in and add up x going from 0 up to 1. So then we'll integrate from 0 to 1 dx. And that will give us the volume of the full oh, you know what? It just said y. It didn't say x had to be greater than or equal to 0. Ah, it does go all the way to the back, right? Sheesh. So I just noticed that. So we would just integrate. All that changes is we would go from -1 up to 1. So we're not limited by x being greater than or equal to 0. It's just y that's greater than or equal to 0. So what we have for the shape is something like this. Right, a little bit longer than that, but that's the idea. Well, the key here again for these is you're integrating your function, and you're going to pick one variable to integrate first. You kind of add it up, and you get this cross-sectional area. So we integrated with respect to y first, going from the x-axis up to the curve. So y goes from the x-axis up to the curve. Y goes from 0 up to the square root of 9 minus 9x squared. Then, once I have that slice, then I add up in terms of x, and x goes from 0 up to 1. Actually, no, -1 up to 1, right? And this will be the volume of that particular solid there. Okay, that is it for this video. Sorry that this one's a little bit longer, and there were a couple of errors in there, minor errors, we were able to catch them. That is it. Post in the comments if you have any questions, or email me, and we can talk about them when we have our class meeting as well.